Welcome to another lecture on design and analysis of algorithms. The topic for today is lower bounds for sorting. Let me begin with a very fundamental, a very basic question. Suppose we just designed an algorithm that takes time f of n to solve some problem, where n is the size of the problem. What would we like to know then? Naturally, a question that we would like to ask is this the best possible algorithm, or can we do something better than this? Here is a possible result we will desire. Okay, we would like it if we can prove that every algorithm for solving the problem must take time at least omega of f of n. Okay, remember, f of n is the time taken by the algorithm that we just designed. Suppose we proved a result like this, what would it mean? Would it be a valuable result? Okay. Well, first of all, this result, if we can prove it, is called a problem lower bound. It is called a problem lower bound because it says something about the problem. It is not really saying anything about a specific algorithm. It says every algorithm for solving the problem must take time at least omega of f of n. So, it is a lower bound on the time taken for any algorithm which solves that problem. Okay. Now, if we could prove something like this, that is, if we could prove that the time taken by an algorithm is equal to the problem lower bound or is equal to within this omega or to within some proportionality constant, what do we know? Well, if we could prove something like this, we know that we have the best possible algorithm. If this equality is exact, then we know we have the absolute best possible algorithm. If this equality is approximate, well, if it is of the form omega, so we know that this bound, that we have the best possible algorithm to within a constant factor. So, this is the main motivation for studying what are called problem lower bounds. So, here is what we are going to do today. So, we will be having a general discussion of problem lower bounds. Then we will consider the question of lower bounds for sorting. So, problem lower bounds, but the problem being sorting. Regarding sorting, I will introduce a model of computation called a decision tree, and then we will prove problem lower bounds on decision trees for the problem of sorting. Now, you may wonder, why do we care about decision trees? Isn't the random access machine or the RAM model which we have defined and which we have been using so far in the course, isn't it a good enough model? Well, it turns out that whatever we do on decision trees is actually quite relevant to the RAM model. So, we will see this relevance. And then we will come to average case lower bounds. Again, we will prove average case lower bounds on decision trees, but again all that will be relevant to the RAM as well. So, let us start with something which we have already studied at least a little bit. Okay. So, we have already defined the notion of putting a lower bound on the time taken by an algorithm. So, here is what we said. Okay, we said that if we have an algorithm A for a problem P, then we will say that it has a lower bound f sub A, where f sub A is a function, if the time for the algorithm A on instances of size n is greater than or equal to f A of n. And of course, we are not worried about every instance, but we are worried about the worst case instance, the worst instance, the instance for which the time is the largest. So, always in this course, we have been stressing the worst case bounds, or the worst case times when we measured the performance of algorithms, and even here we are doing that. So, we are asking what is a lower bound on this time, the time of the worst instance I. Okay, of size n, of course. So, it will be f A of n. This is what this means. This is what it means to have f A as a lower bound on a problem P, on an algorithm A for a problem P. Now, of course, it is customary to say that this inequality holds only for large enough n. So, there is actually a clause over here which says for all n greater than n naught, where n naught is some number. Okay. But let us not worry about too many technicalities right now. The typical way we prove lower bounds is by constructing instances I which take a large time. So if we have an algorithm, we look at where the algorithm is weak, so to say, and we construct instances which show that the algorithm must take a long time on that particular instance. So that gives us a good value of f sub a, okay, f sub a of n. And we have to do this for every instance, every size, instance size. If we can do that, then we can construct this lower bound function. Next, we'll look at problem lower bounds. A problem P is said to have a lower bound f if every possible algorithm has lower bound f. Okay. So this statement has to apply, but it has to apply for all possible algorithms for this problem P. Here is the more algebraic statement. So notice that this part, okay, is just similar to this part, okay, and now we have an additional quantification. We are saying that this must hold even for the best algorithm. So the algorithm which takes the minimum worst case time must have time bigger than f of n. Of course, if the best algorithm has time bigger than f of n, then clearly every algorithm will have time bigger than f of n. So this is what it means for f to be a problem lower bound for this problem P. How do we prove such bounds? Okay, now we have to construct bad instances, okay, instances which show that the time taken is large, okay. But we have to construct them not only for all problem sizes, but for all algorithms as well. And of course, the instance, it need not be the same instance for all algorithms. It could be that for one algorithm, it is one instance which is bad. For another algorithm, it is another instance which is bad. That is okay. But somehow we must give a construction which shows that for no matter what algorithm you give, here is an instance on which it will take a long time. We may not do this directly, but at least indirectly something like this has to be proved in order to prove a lower bound over here. Here are some trivial lower bounds that we can prove. Okay. Most problems have an omega of n lower bound, okay, where n is the instance size. I say this is trivial because no matter what algorithm is used, the algorithm at least has to read all the input. The input has length n, and therefore omega of n time has to be taken. So in that sense, there is nothing clever about this, and it by and large applies to every problem. Okay. There could be some problems where it may not apply, but those are probably not very interesting problems. Okay. What about non-trivial bounds? It turns out that on random access machines or RAMs, proving non-trivial bounds is actually very difficult. And here are some of the reasons. Basically, when we assert a problem lower bound, we are saying something about every possible algorithm. Now, on RAMs, the space of all possible algorithms is really huge, and it is tricky to analyze. Okay, so a single problem may have lots and lots of algorithms. Enumerating those algorithms or analyzing them in some structured fashion is often a very tricky business. It's tricky because of some of these reasons. A RAM has many instructions. A RAM has instructions to do all arithmetic. Okay. They can be composed to do more complicated things. You can take logs. You can exponentiate. You can take trigonometric ratio. You can take trigonometric functions. Okay. You can do all such things with RAM instructions. There are also many control flow patterns. There is looping, there is recursion. And so if I give you a RAM program, analyzing it is pretty difficult. And saying something about all possible RAM programs is even more difficult. So here is what is typically done. Okay. So we define a simpler computational model, okay, which say doesn't have that many instructions and which doesn't have that many control flow patterns. Okay. So we define such simpler computational models, and then we analyze that. Okay. It will turn out that on such models, the space of programs or space of algorithms is actually fairly small. Okay. Well, it's never really small, but it's much easier to visualize. So that's what we are going to do next. So here is one such model. This model has been introduced in the context of algorithms such as sorting. So it will have instructions which are relevant for sorting, but which are perhaps not very useful for other problems. But since we will consider this model in the context of sorting, this model will actually be a reasonably good model to look at. So here is what the model looks like. Okay. So the input to every algorithm is always going to be a sequence of numbers. Okay. And we are not going to worry about inputting those numbers. We'll assume that those numbers have already been read and they are already stored somewhere in the model. A program for this model is a labeled tree. Okay. So every non-leaf node has labels of the form I:j, where I and j are integers. Okay. I'll tell you exactly what a label means in a minute, but let me just describe the model first. Each edge also has a label, and the label could be any of these relational operators. Leaf node labels are the values that are going to be printed. So that is what a structure of a program is. So here, for example, is a program which will be used for sorting 3 numbers, which can sort 3 numbers. I haven't told you exactly how it sorts 3 numbers. I will tell you that, but I just wanted to give you a picture for the program tree model that I just mentioned. Okay, so as you can see, the label over here is 1:2. This edge is labeled with greater than, and so on. And the leaf is labeled with 312, which is what it is going to output, okay, as per the execution model, which I'll describe next. The execution in this model begins at the root. Okay. At any node labeled I:j, input xi, which came over here, is compared with input xj. The result of this comparison is some relational label. Okay. So it's either less than, equal to, or greater than. And based on that result, the execution follows the appropriate branch. So say, for example, the result is less than, then we will look for branches having either the label less than or the label less than or equal to branch on that. We will require that only one out of less than or equal to and less than be a label present on the outgoing edge. This is because we want our algorithms to be deterministic. So once we make a comparison, we want a unique path to follow outwards. When the execution arrives at any leaf, the label of the leaf is output. So let's try this out for this program that we have drawn over here. So as I said, this program is going to be used for sorting 3 numbers. So let's say the input instance is x1 equal to 20, x2 equal to 30, x3 equal to 10. As we said, the execution starts by looking at the root, by starting at the root. At the root, we compare x1 with x2. So in general, if the label is I and j, we compare xi with xj. So when we compare x1, which is 20, with x2, which is 30, we discover that x1 is smaller. Okay. So if it is smaller, then we follow this branch. So we follow this branch and we arrive at this node. And when we arrive at this node, we have to act according to the instruction represented by this node, which is to compare x2 and x3. x2 is 30, x3 is 10. So therefore, we find that x2 is bigger than x3, and therefore we follow this branch. Then we perform the instruction represented by this node, which requires us to compare x1 and x3. So x1 is 20, x3 is 10, x1 is bigger. Okay. So we arrive at this node, and at this node we just output. So we output 3, 1, 2, which is representing our conclusion that x3 is the smallest, x1 is the next smallest, x2 is the largest. And indeed, you will see that x3 is 10, which is the smallest of 10, 20, 30, x1 is the next largest, and x2 is the largest. So at least for this instance, we have checked that this decision tree, which represents a sorting program, has in fact correctly sorted this input instance. Notice that if I increase the size of my input, I will have a different program. I will have to have a different program. This is unlike what we usually do in the RAM model, but that's okay. We are going to allow that in this model. To complete the description of the model, let me just mention that the time taken by the program is simply the number of comparisons performed for each instance. Okay. The worst case time is equal to the length of the longest path in the program tree, right? Because if you take that, if in any execution you follow that path, that's the time you will end up spending. Likewise, we can also define average case time. So here, the input instances will be chosen randomly with equal probability from all possible input instances, or we are just asking for an average time over all possible input instances, and therefore we should just consider all possible root to leaf paths, and it's simply the time for each such path is its length, and so the average case time is just the average root to leaf path length. So notice that the time taken has a very nice graphical interpretation in this model. So now here are the main claims that I'm going to make. The first claim is that sorting will take time n log n in the decision tree model. This claim has to be understood properly. This claim says that no matter what algorithm you use, and by algorithm we mean no matter what tree you use, because that's the space of all possible algorithms, no matter what tree you use, the time taken will be n log n. The length of the longest path in the tree will be at least n log n. So notice that this is already a non-trivial bound, because a trivial bound would be omega of n. We'll prove this in a minute. But I first want to relate all this to a RAM model, because a RAM is, after all, what we use every day. So a definition first. A RAM sorting algorithm is said to be comparison based if the only operations it performs on keys are comparisons and copying. So if you go back and think about the sorting algorithms that you have seen, there is a good chance that most of them are in fact comparison based. Take heap sort, for example. The only operations you do on keys are you compare two keys, and maybe you copy them. Similarly for merge sort, similarly for insertion sort, similarly for shell sort if you have studied that. So in fact, most of the algorithms that you have studied probably are comparison based algorithms. And it turns out that they are actually quite nicely connected to decision tree algorithms. So here is the claim. Let A be a comparison based RAM sorting algorithm. Then there exists a decision tree sorting algorithm C that performs exactly the same key comparisons as A on every input instance, in fact in the same sequence. So this means that the time on this decision tree model is intimately related to the time on the RAM model also for this class of algorithms. The final claim says every comparison based sorting algorithm on the RAM must take time n log n. So this is where we have finally come back to the RAM. Okay. So here is a non-trivial result, not about all sorting algorithms, but for comparison based sorting algorithms. For comparison based sorting algorithms, we have proved that the time taken must be at least n log n. Well, we have claimed and we will have proved this in a minute. So let us try proving this first. This in fact turns out to be the crux of the matter. So we want to prove that sorting takes time omega of n log n in the decision tree model. So we are going to start with a certain input x. Okay, remember x is that sequence x1, x2, x3, and let us suppose we have a sequence x which is a permutation of the sequence 1 through n. Permutation is just a rearrangement of that sequence. Okay, so x is pi of this. Okay, so what can we conclude from that? Well, then 1 to n must be pi inverse of x, right? So if I apply the inverse permutation on both sides, I will get pi inverse over here and 1 to n over here. So notice that when we do the sorting, we actually are supposed to compute this inverse permutation. So every leaf, okay, so the answer essentially must be pi inverse 1, must be pi inverse. Okay. So essentially pi inverse must appear as the label of at least one leaf, essentially. Because that leaf must have somehow identified this permutation, and only then can it name how this permutation can be unscrambled to get 1 to n. Okay. So pi inverse must appear as a label of at least one leaf. Now this holds for all possible permutations, not just a particular pi. How many permutations are there? Well, there are n factorial permutations, and therefore there are n factorial leaves. So this is the key insight. We have proved that this tree, the algorithm tree, must have at least n factorial leaves. Each node of the tree can only have at most 3 outgoing edges. Well, there are so many relational operators which we mentioned. Okay, but we cannot use them simultaneously. As I mentioned earlier, we can only have, so here is a node. If we have less than here, then we cannot have less than or equal to over here. We must have something which is disjoint from this. So the only possibilities are we have greater than or equal to, in which case we can only have 2 labels, but only 2 outgoing edges, or we could have 3 outgoing edges, less than, equal to, and greater than. So at most 3 outgoing edges are possible. Now each tree node can only have 3 outgoing, if it can only have 3 outgoing edges, then the height must be log of the number of leaves to the base 3. The height of a ternary tree is log of the number of leaves to the base 3 at least, and therefore height must be log of n factorial to the base 3, because n factorial is a lower bound on the number of keys, on number of leaves. Turns out, however, that if we are only using permutations of this, then we will never pass through this equality edge. So which means the n factorial leaves must be accessible only passing along these strict inequality branches. So which is as good as saying that if our input is a permutation of 1 to n, then we are only considering a subtree whose degree is at most 2, and therefore the height is at most log of n factorial to the base 2. Okay. But log of n factorial to the base 2 can be now thought of as, if you expand out the product, you can see that it is this, and that this is actually easy to see. So let us do that. So n factorial is n times n minus 1 times n minus 2 and so on. Somewhere in this we are going to have n upon 2, and then there are going to be some more terms over here. But all these numbers you can see are going to be at least n upon 2. And how many such numbers are there? Well, there are n over 2 numbers, each of which is at least n over 2. Okay. So therefore, n factorial is bigger than n over 2 to the power n over 2. So what we now have is that log of n factorial to the base 2 is at least log of n over 2 to the power n over 2. Well, we can simplify this and we get n over 2, this is equal to n over 2 log of n over 2, and therefore this is omega of n log n. So what we have done so far is that we have proved this. Now we want to look at the next claim. The next claim is the one which relates comparison based sorting algorithms in the RAM to decision tree sorting algorithms. Okay. So the claim says, let A be a comparison based RAM sorting algorithm, then there exists a decision tree sorting algorithm C that performs exactly the same key comparisons as A on every input instance. Okay. So we are going to prove this, and the proof is going to be actually constructive. So what we will do is, we will assume that we have been given this algorithm A, which is a comparison based RAM sorting algorithm, and then using that we will construct a decision tree sorting algorithm C. And we have to make sure that C performs exactly the same key comparisons as A does on every input instance, and also in the same sequence. Okay, so this is what we are going to do. We are going to construct C from RAM algorithm A. So let me remind you what C looks like. So C is going to be some root node, maybe some branches, okay, maybe nodes over here, and so on. So if I tell you how these things are going to be labeled, then I am done. Okay. So let me tell you the edge labels right away. The edge labels are going to be less than over here, equal to over here, greater than over here. So let's keep it really simple, and similarly subsequently. But I have to tell you what the label over here is going to be. So the question is, how do I do that? So it's going to be some I colon j, but I have to figure out what I colon j it is going to be. And here is the key insight in figuring this out. The main idea is that which keys are compared first by A is our RAM algorithm, does not depend upon the key values. Why is that? Well, A is going to read things and then it is going to compare. It is not going to look at the keys and base its decision on which keys to compare on the value of any key. Because in fact, the value of any key does not really come into the control structure of A, okay, other than in the comparisons that A does. So if A does a comparison, that's the only time when A can actually peep inside a key value. So clearly the first time that A peeps inside a key value is the first time A does a comparison. Okay? And in fact, that which keys it compares is going to be the same. No matter what the values of the keys are. So Ij can be determined by examining the algorithm A. We just look at the code of A and we'll know which keys A is going to examine first. So whatever they are, we can write that down over here, I colon j. We find the numbers, we find actual numbers I and j, and we put them down over here. Okay. So I claim now that whatever numbers I and j we put down over here, okay, they will be the same no matter what the values of the key are, and that is what I just explained. So next, we want to find the labels of, say, this node over here. Okay. To do that, here is what we consider. Okay. So suppose I is an instance in which xi is less than xj. Okay. Now we are going to examine the program of A to determine which keys are compared in the second comparison for this instance I. Suppose xk and xl are compared. So those values, those k and l, we will put down over here. Okay. So now what's the idea? So for instance I, what will happen? The first comparison will be this. Then of course in the decision tree, this will be the branch taken, and the second comparison will be this. So instance I, in fact in instance I, the first two comparisons have been the same in the decision tree as they have been in our algorithm A. So far so good. So far we have built this part of our tree, and indeed in this tree the comparisons made on this instance are the same as the comparisons made on the instance in our RAM model also. But let's consider another instance I prime. What will happen in that? Okay. So if we consider another instance I prime in which xi is less than xj, what will happen? Okay. Which keys will be compared next? I claim that even in that case, the keys to be compared will just be these xk and xl. Why is that? So let us examine this. So here is an execution of I, and here is an execution of I prime. So we somewhere we start execution, we compare xi versus xj, and we know that the first comparison is the same in both, and so we compare xi versus xj. Then we do some instruction over here, and we compare xk versus xl. Okay. So when we do these comparisons, the question is what will happen over here? Okay, I claim that if in these instructions no key is even touched, then exactly the same instructions will be executed over here. Okay. Why is that? Well, the control flow can change only if there is a comparison, and if that comparison has a different result. So in this entire part, there has been a comparison with keys, but the result over here is the same as the result over here, because in both cases we said that xi is less than xj. So during this entire portion and this entire portion, wherever there have been comparisons, the comparison outcomes have matched, and therefore the instruction which is going to be executed over here is going to be exactly the same. And therefore we will also compare xk and xl over here. So which means even for this instance I prime, k and l, xk and xl will be compared, and therefore we can put down the label of this node as k compared to l. Now we can generalize this. So the general pattern is we have constructed some super tree of C. How do we extend it? Okay. So we have constructed something like this, okay, and so in general we might have had constructed some path, okay, and then we want to extend this path outwards. How do we do that? Okay. So here is the observation. The label of a node can be determined by considering an instance consistent with the labels on the path till the node. So I want to determine the label of this node over here. How do I do it? Well, I look at instances on the path from the root, I look at the labels on the path from the root to this node, and I construct an instance which is consistent with these labels. So which means that xi must be equal to xj, and then whatever that label is over here, the corresponding keys over here must satisfy this label, and so on. And then we simply look at the algorithm for A and ask what is the next comparison that is going to be made, and we put down those labels over here. So we have constructed an instance which is consistent with the labels along this path, and we look at the algorithm and decide what is the comparison that is going to be done by that instance, done by the algorithm on that instance. So if the comparison is between some xp and xq, we put down p:q over here. Okay. So exactly like what we did in this case, but just more general. So in fact, in all such instances which are consistent with the labels along this, you can argue in exactly the same way that xp will be compared with xq, and that will fix the label of this. If it turns out that the information which has been gleaned along this path is enough to determine the final sorted order, and because of which the algorithm does not do any comparisons at all, then well, we simply take that sorted order and put that as the label and make that a leaf. Now, the important point is that we have constructed our decision tree algorithm in this manner, and by construction, because of the care we took in the construction, you can see that C performs exactly the same key comparisons as A does in exactly the same sequence on every instance. So this finishes this claim. So now I want to argue that every comparison based sorting algorithm on the RAM must take time n log n. But this is actually fairly straightforward. So suppose some comparison based RAM algorithm takes time t of n. What do we know about comparison based RAM algorithms? By the claim that we just proved, we know that there must exist a decision tree algorithm taking time at most t of n. But the first claim tells us something about decision tree algorithms. The first claim says that the time taken by the decision tree algorithms must be at least n log n. So t of n had better be at least n log n. But then this t is the same as this t, and therefore comparison based RAM algorithms must also take time n log n. Okay. So we have proved this claim. Okay. So notice that in a single claim we have proved a lower bound on a variety of sorting algorithms: heap sort, merge sort, shell sort, insertion sort, and many other algorithms which you have not even thought about, but which if they are only comparison based, then this lower bound will apply to them. Next we turn to average case complexity. So basically we are going to ask the question, what is the average case? Can we put a lower bound on the average case complexity? So that on the average time to sort, not just the worst case time. So this actually follows fairly easily, just based on structures, on some properties of trees. So here is the first claim. Okay. If a tree has k keys, then there exist at least k over 2 keys at a distance log k over 2 from the root. Okay. Why? Well, there can be at most square root k leaves at a distance. Just like worst case, we can use very similar arguments to prove bounds on the average case complexity of sorting as well, on the decision tree model, of course. And of course, that will imply some lower bounds on comparison based sorting algorithms as far as their average case complexity is concerned. And these bounds really follow very simply from some properties of trees with respect to the relation between the height of the trees and the number of leaves. So here is the first claim. If a tree has k leaves, then there exist at least k by 2 leaves at a distance at least log k by 2 from the root. Well, here is the proof. There can be at most 2 to the L leaves at a distance L, which means there can be at most 2 to the power log k whole thing upon 2 leaves at distance L, and this is nothing but k to the half, or square root of k. So that is what has been claimed over here. Okay. The rest of the leaves have to be at a larger distance, and in fact this says that as many as k minus square root k have to be at a larger distance, whereas what is claimed over here is just k by 2. So the claim is very easily proved. In fact, you can prove something stronger. But once we have that, we can prove the following. We can prove that the average path length, okay, average is taken over all leaves, is at least log k upon 4. Okay. Why is that? Okay, let's count what the total path length is. Okay, the total path length we are going to calculate first for these leaves which we talked about. So there are k over 2 of them, and each has a path of length log k upon 2. So the total path length just for these k over 2 leaves is at least this much. So now the average is going to be a kth fraction of this, and therefore it's simply going to be this k factor will drop out, this 2 and this 2 will give us 4. So it is going to be log k over 4. From this it immediately follows that the average time for sorting on decision trees is n log n, and here is why. Every algorithm tree has n factorial leaves. Okay. Thus average path length is bigger than, by this claim, log of the number of leaves or log of n factorial upon 4. But log of n factorial upon 4 is n log n. And therefore, average time for sorting on decision trees is this much. And this means that the average case time for all comparison based sorting algorithms, say heap sort, merge sort, shell sort, all of these is n log n. Okay. So when we studied average case complexity of quicksort, we proved that although the worst case complexity for quicksort was n squared, the average case was n log n. So so in a similar manner, it may be conceivable that heap sort may have worst case complexity of n log n, but its average case complexity is just n. It might have been conceivable, but this result shows that the average case time for heap sort is also going to be at least n log n. And similarly for merge sort, shell sort, and any other comparison based sorting algorithm. Okay, so now I want to conclude, and here are some remarks. First, some implications of the lower bound on comparison based sorting algorithms in the RAM. So here is an important implication. So if I want to sort faster than n log n, what do I know? Well, I know that I must use some other operations besides just comparisons. If I limit myself to just comparisons, what happens? Well, there is a decision tree algorithm which mimics the RAM algorithm, and therefore I am stuck to a lower bound of at least n log n. So I must use some other operations besides comparisons. Are there such operations? There actually are. So in fact, a popular sorting algorithm called bucket sort does exactly this. The main operation it performs is that it uses the key values as an index into an array, which was not allowed in comparison based sorting algorithms. So here is the main claim. If the keys are integers in 1 through r, in the range 1 through r, then sorting time is at most n plus r. So I'll just give the algorithm as the proof. So first we are going to build an array of buckets b1 through r. So these buckets will be initialized to null. So that will take about r time. Then we take key xi, okay, and we insert it into this bucket b of xi. So b of xi can be computed in constant time. So in constant time, we keep a list over there and we insert this key into that list, and we do this for all the keys, for all I. So now all keys are now into their buckets. Now for I equal to 1 to r, okay, we go visit each bucket in turn and we print out the contents. Clearly, we will print out the contents in increasing order. What is the time taken? Well, the insertion time is proportional to the number of keys. Okay, so because of this statement, the time to initialize the array of this B array is going to be r, and printing out the answer, well, we have to visit every element of the array, and we also have to visit every key which has been inserted in some bucket. So the time is going to be O of n plus r. So the total time is going to be n plus r, O of n plus r, and this is going to be faster than n log n if r is small. Okay. In fact, this is not the only range. If you have somewhat bigger ranges, say 1 through r squared, a slight modification of this will in fact do the job. The second concluding remark that I want to make is that not only sorting, okay, but you can use the decision tree model to study several other problems. Okay. So the other problems are, say, merging, and this will figure in the exercises which I will show later, and also things like finding duplicates, and this is going to be the topic in the next lecture. Okay. In fact, let me say in conclusion that we can extend this decision tree model. So I want to go to my second concluding remark, which is to say that the decision tree model can be used to study other problems as well, not just sorting. Okay. So in particular, it can be used to study merging problems, which I guess you might think as very similar to sorting. It can also be used to study problems like finding duplicates. Or it can also be used to study problems such as putting lower bounds on the time to calculate the intersections between two given sets. Now this problem might seem like rather different from sorting, and it is actually perhaps somewhat surprising that decision trees can be used for this. Nevertheless, they can be used, and in fact we will see the finding duplicates example in the next lecture. I will also state that the idea of decision trees, the general model of decision trees, can be extended somewhat, so that rather than just allowing comparisons, you can also allow some arithmetic inside it. And so the lower bound model can be made somewhat stronger. In any case, we have seen some lower bound results, and we will continue this with the next lecture. Thank you.